Okay. So are you able to see the screen?
Yes, sir.
Okay. Thank you. So we were discussing about that satellite subsystem. So in that we have come across the antenna subsystem. So for that we were reviewing some of the basics of antennas. So in that, like the basic mechanism of the antenna is that it is a transducer which converts electrical energy into electromagnetic energy. So at the transmitter, whatever from the transmission line, whatever electrical signals are coming, so those will be slowly converted into the electromagnetic signals or electromagnetic waves at the transmitter and the receiver. So when this free space 3D waves are coming in the medium or in the free space, so generally we assume free space, but there is some atmosphere around us. So in that, if this wave, so it is 3D wave. Why it is 3D wave? Because there are three components. One is the EX and HX, or electric field component, magnetic field component, and it's also varying with respect to time because it's a time varying phenomenon, electromagnetic wave. So sometimes that another Z is also there, that becomes the fourth dimension. So but here it's only a 3D wave. So when these waves are coming or they are traveling in the free space, if you have a receiver which is suitable for this frequency, then that antenna will be able to receive these signals and convert them back into the electrical energy. So that is this first definition of antenna. So it is a transducer which is converting from one form of energy to another form. So this is the basic definition, or some other definitions are also there for the antenna. That is, it is a impedance matching device. So like when the signal is coming from the transmitter or the transmission line, it has to be matched into the appropriate load. So if the load is not appropriate with respect to the source resistance or source impedance, then we will get reflections, right? So the whole point of maximum power transfer theorem is to match the impedance at the source and the load so that all the wave will be transported to the load without any reflections. So if this impedance is not matching, so sometimes when we speak with new people, or we tell that our wavelengths are matching. So how our wavelengths are matching? Because we are thinking in the same direction or same type of what is that? Same type of thinking pattern is there. So our thoughts are closely matched. So that is the meaning behind that wavelength is matching. So similarly here also we want to match the impedance in any maximum power transfer theorem. The aim is to make the load resistor equal to the source resistance so that it grasps everything that the transmitter is trying to send it. If you don't match that impedance, then obviously it cannot grab everything which the transmitter wants to give it, and some of it is wasted. So as simple as that. So you can imagine like a pipe. Suppose if this side you have a bigger pipe, and another side if you have a smaller pipe. So if you try to connect them, then the water may escape from some other portions which this pipe is not fitting. So like that. So yeah, so one more name for this antenna is aerial. So all these things we were seeing, and when the radiation is possible. So suppose if you have a uniform current carrying conductor where all the charges are moving at uniform velocity, then you cannot expect any radiation to occur. So there must be some acceleration of the charges, or there must be some uh, like change of velocity. So we should somehow break the periodicity of those charges. So either you create some reflections, so or you change the shape of that structure so that the velocity is changing, or you feed a sinusoidal signal at this, so that these charges are moving periodically back and forth. So that is this one. So here it's indicated like transmitter is giving a sinusoidal signal. S- and one more option is to flare like this, so to create a gradual transition from the guided medium to the unguided medium. So even if you create like this, so then also you can reach that acceleration effect, so then it will be radiated. Right. So then there were some differences between the mechanical or sound waves and the light waves. So this we have seen. And important thing about this pointing vector is it is pointing the direction. Name itself is pointing is the name of scientist, but it serves the purpose. Like it is pointing in the direction where that electromagnetic wave is traveling, and obviously it is proportional to the both of these electromagnetic electric field and the magnetic field. So that's why we generally write pointing vector P is equal to E cross H, which is given as the cross product of E and H. So because, yeah, it is third orthogonal to both of these fellows, right? So then we have seen the typical parameters of the antennas. So for understanding the type of antenna which we need in the satellite communication, so first we should know what are the parameters of that antenna. So these are some of the main patterns. One is the radiation pattern. So radiation pattern gives the three-dimensional uh, distribution in which directions the power of the antenna is going. So there may be a omnidirectional antenna. So this isotropic antenna is called as omnidirectional. So it is radiating equally in all directions, always used as a reference antenna. So then there are some directional antennas. All other antennas except the isotropic, they are directional antennas, and their power is radiated only in few directions. So they are directional antennas. So almost all the antennas have one main lobe, that is the main direction in which they want their energy to go. Or at the receiving end, it is like the directions from which this antenna wants to receive. So suppose something is coming from this direction, the antenna is not much interested to receive the things that side. So in that direction, it does not have the main lobe. It has only side lobes. Right. So all these are directions, and I told you like side lobes are these small things which are oriented in other directions. So little energy of the antenna goes wasted in those side angles also. Those are called side lobes or side beams. And then sometimes there is a back propagation or back lobe radiation, which is also an undesired effect. Okay, so all this more or less we have seen. Then beam width is how much sharp this main beam is. So if it's very sharp, then beam width is very less, and we say that antenna has very good resolution, very good directivity. It's able to see in a particular direction very well. So that is a good point. If you want a directive antenna, you should have very less beam width. So this is not spreading in different directions. It's as much concise and as much focused. So then it is better to, like, whenever you want more directivity, whenever you want your signal to go only particular direction. So generally we do this in deep space communication. So we want our signal to go only in one particular direction. So we need high directive antennas. So then this parameter, like similar to the amplifiers, we have 3 dB bandwidth there. Here it is 3 dB beam width. So what we do is this half power points we take. So where this uh, highest value of the power is 1, then half power points you note down, and what is the angle between those two, that is the half power beam width. Then there are some directions where the antenna does not radiate anything. Those are called as nulls of the antenna. So then another parameter is FNBW, first null beam width, or beam width between first nulls, BWFN. So these two parameters tell us how much directive that antenna is and how much resolution it is having in terms of the angular or spatial resolution. Okay. Then we were seeing these types of antenna. Let me see. Okay, still today also very less people are there. Okay, so I hope you have seen your cat paper and okay. Okay, so these are the different types of antennas which we have. So this is called as a dipole antenna. So the feed is in the center of this. Control P, no, control L. Okay, wait. Okay, this is okay. So this center part of this element, this is a dipole antenna. So these dipole and monopole, they are called as wire antennas. So they have only a wire and structure is very simple. So the wavelength is half wave, like the length of that or the dimensions of that antenna are like half wave. So that generally we call it as half wave dipole. So that is a very famous antenna, first smallest and easiest antenna to make. So this is the dipole. Okay, so here I am talking. So if you see above it, there is one pole, lambda by 4. This is lambda by 4. Overall, it is lambda by 2. So that's why we call it as half wave dipole. Okay. So half wave dipole, and before this there is a monopole antenna. So monopole is like, suppose if you have the feeding here and it will be only above this. So only lambda by 4. So this bottom part won't be there in the monopole. Only one uh, wire will be there towards the top, and the length of that antenna is lambda by 4. So we call it as quarter wave monopole. So okay. So these are the two fundamental antennas, dipoles, or they are also called as wire antennas. And what happens is, I told you that there should be a impedance matching. So in the free space, impedance is some how much? Free space impedance, I guess it is 377 ohms. And this dipole antenna has a radiation resistance of some 75 ohms, let us say. So if you have 75 ohms, these two impedances are not matching. So there will be some reflections, and radiation efficiency of this dipole is very less. So if you see the radiation efficiency, yesterday we have told like how much is the source giving and how much you are able to successfully convert it into radiation. That is the radiation efficiency or the antenna efficiency. So if these impedances are in this manner, this is this side 75 ohms and free space impedance is this much. So then 120 into pi is how much? This is 120 into pi. So I guess it's 377 ohms. So this is the free space impedance, and radiation resistance is a term which is also an antenna parameter. So actually that resistance is an imaginary resistance resistor. So it's not there in practice. In reality, that radiation resistance is not there, but it is like uh, what if so it's the resistance which this antenna is facing in order to radiate the things, radiate the energy into the electromagnetic medium. So it's not there, it's a imaginary thing, but that effect is available. So had if there been a resistance of this much 75 ohms, how would that signal propagation take place? So that is the effect which this phenomenon brings in. So therefore we consider the radiation resistance. So this side it is 75, that side it is 377. So not matching. So dipole has very less efficiency. So then what they have done is they have gone for this folded dipole. So folded dipole is looking like this. So the radiation resistance depends upon number of folds which this has. So if you go for 4 folds, then it will increase 4 into 75 like that. And suppose if you have 2 into 75, so slightly they will get better performance. So suppose if you have 300 ohms as the radiation resistance, and this thing does not change, free space impedance is always 377 ohms. So it's a better match compared to 75 ohms and 377 ohms. So therefore folded dipole has better radiation efficiency. So and then there is another particular type of antenna which is called Yagi-Uda antenna, which is very famous. So this is a reflector here, then one director element, main element, and followed by the another. So this is the main radiating element, and it radiates in the forward direction. Whatever backward radiation is there, that will fall on this reflector, which is this folded dipole, this one, and it will again send back this energy into this direction. So you might have seen this kind of arrangement, like not this one, this is helical antenna. This one you might have seen on many rooftops earlier when Doordarshan was there. We used to have this kind of antenna on every household. So this is called as Yagi-Uda antenna, very famous. Some people also write Uda Yagi antenna based on. So this, I think Uda was the professor, Yagi was the student. So there is some controversy, like this person Uda was some Japanese, so he did not write the research paper. Yagi was comfortable in writing English papers, so he has written quickly and published. So that's how it has become Yagi Uda antenna. Some textbooks they write Uda Yagi antenna. That is okay. That is not our problem. Okay, so similar to this, we have a horn antenna. So this one is a horn antenna. So what we do in this horn antenna is it is a flayed version of a waveguide. So till here it is waveguide, and slowly we flare the waveguide structure so that we can get a electromagnetic radiation, and we will get wide coverage. So if you are aiming at a wide coverage, then it is better to go for a horn antenna. So this is like flared, all this is metal only. Uh, so something like in the sound we have that loudspeakers, right? Near Ganesh and Durga festivals, we have that, or in the election campaign, they have that big mic, which is like this flayed. Why they have it flayed? Because it travels in different directions. So we are travel in different directions using that structure. So same idea is copied here in terms of the electromagnetic waves. So they want the similar flaring is done. So here, of course, you can see it is strictly square type, but slightly we can make it conical or circular, similar to the loudspeakers which are there in the market. So then we can expect the wide coverage. And those are the horn antennas. So other types of antennas are not much relevant to the satellite communication. These loop antennas and helical antennas and patch antennas, they are not so much important. So then we have corner reflector or parabolic reflector. So they have this kind of structure, the general DTH, Tata Sky kind of things. So what they operate is there is an input coming from here through the transmission line, and it is first fed to this horn. So here one horn antenna is there, small one. Then what it does is it creates uh, its radiation will fall on this parabolic dish. So this is called as parabolic dish. And what happens is these will be spherical wavefronts when they are falling on this reflector surface, and after reflecting they convert into the plane wavefronts and they get radiated. Okay, so sometimes this direction of this horn is kept this way, so that it is called as corner reflector. So this horn is kept in such a way that its radiation falls this side like this. So once they are reflected, they go above in this direction to the satellite. So same, these are all antennas follow the principle of reciprocity. So whatever is possible at the transmitter, that is easily possible at the receiver also. So if you are designing a receiving antenna, it can easily collect the plane wavefronts which are coming from the satellite and convert them into spherical wavefronts and give to this horn. So this horn antenna, and that horn antenna will convert into the electrical signals and give to the transmission line. So that's how you are getting all that DTH and Tata Sky, Airtel. So antennas follow the principle of reciprocity. So symmetry is also there. So whatever is possible at transmitter is possible at receiver. So then another type of arrangement is called as the Cassigrain feed. So Cassigrain feed is like, some people are having a problem that this feed horn is taking away some of the radiation. Like once these are reflected from here and these plane wavefronts are coming. So if this horn is bigger, then it uh, kinds kind of acting as an obstacle to those waves. So they change this horn to this side, and here they put a hyperbolic sub reflector. Uh, and whenever from this horn the signals are falling on this hyperbolic subreflector, they get again reflected to this major parabolic dish, and then they are sent out into the free space. Okay, so this patch antenna is very famous for smartphones and low form factor devices and 5G, 4G, IoT, all those things. So I don't know how many people are listening, because before CAT there was good participation. Now I don't think so much. If you have any questions, you can ask.
Sir,
Yeah,
sir, while explaining dipole, you had said that the length of the antenna is lambda by 4 and it is called quaternary antenna. So, like, the formula for the length of an antenna is always lambda by 4. Why is it specially called quaternary? Why not any other antenna called quaternary?
quaternary, golden jubilee, no, not that. Quarter wave. Okay, quarter
Yes.
wave is generally we want the antenna dimensions to be proportional to the wavelength. So either it should be lambda or lambda by 10 or lambda by 4, like that. So this one particularly, it is if you have only one side of this, then it is called monopole. In particular, if its length is lambda by 4 or the height of the antenna is lambda by 4, then we call it as quarter wave monopole. So here also dipole is a general thing, but if you are able to maintain this upper arm as lambda by 4 and below arm as the lambda by 4 again, then overall length will be lambda by 2. For that, we call it as a half wave dipole. So these are I didn't get your question, what you were asking. So antennas have different dimensions. Like some of them are lambda, some of them are lambda by 10. So in modulation techniques or in analog communication, we take it as lambda by 4. But there also some textbooks write antenna length as lambda by 10, and they will try to prove that modulation is necessary. So that is our wish. Overall, it should be proportional to the wavelength. So that is the main idea between the antenna dimensions.
Okay, sir.
Okay. Okay. So if you see most of our students, MTech students at least, they try to sit in that microwave lab, and there is two, three softwares are there, HFSS, AWS and CST Studio. So they try to do all this design of a patch antenna, and they visualize different waveforms and parameters. Okay, so then this is polarization of antenna, which is also important, but you can just see these diagrams. Vertical polarization is the electric field vector is oriented in the vertical direction, and here if it's horizontal, then it's the horizontal polarization. Basically, polarization is the orientation of the electric field vector. So then again, if you see the top view of this, if the locus of that is like a line, then it is linear polarization. If the locus of that is like circular, so if you see this bottom one, so this is like spiral. So if you project all of them onto the floor, then what is it, locus of that is a circle, then it is circular polarization. This is elliptical polarization. So yeah, so that is based on the situation, they will try to use different types of polarization, but generally linear polarization is famous. So sometimes the signals can take advantage of the dual polarization. We can send some signals in vertical polarization and some other signals in the horizontal polarization. So if you have any time seen any TV channel, whenever they are launching a new TV channel, at the scrolling, let us say they are starting a new channel in Z network. So in all those Z TV channels, they will give the scrolling like new channel Z something Z G plus, let us type. So G plus is one new channel which they are starting. So they will give the information to the cable TV operators, like what is the frequency in which this channel is available. So frequency band they will give, like where you have to tune for that, 6.625667 gigahertz, something like this. Then they will also mention what is the polarization to be followed in order to receive that, left hand circular polarized or right hand circular polarized. And they will also give what is the transponder capacity, or so different details which are relevant to the cable TV operator will be provided there. So he will try to see all these things and connect to that channel. And once he has connected, then those things can come to our homes. So that is the earlier phase, like when the set top box things were not there in the olden days. Okay. Okay, so then these are the types of propagation. I think some of you who have studied in CBSE 12th class, you know these things. But generally there are three modes of propagation. One is the ground wave. So ground wave is like the waves follow according to the curvature of the earth. Like uh, so they get transmitted, like they are reflected from the earth's surface and slowly graze through the earth's surface. That is the, they follow the curvature of earth. So it is suitable for frequencies which are below 30 kilohertz. These are very low frequencies. And if you slightly increase the frequencies, then he says that they undergo severe attenuation, so ground wave propagation is not possible. So if you have very low frequencies, then they can follow that Earth's curvature and they can propagate through the ground wave propagation mechanism. So then if you have higher frequencies than what you are supposed to do, then you are supposed to go for this skywave propagation. So in the skywave propagation, what we do is we send the signals till ionosphere, and from the ionosphere, these signals get reflected back to the Earth's surface. So this is how the AM stations work in entire world. AM stations are based on most of the AM stations are based on this ionospheric reflection. So this is suitable for frequencies which are below 30 megahertz. So above that, what will happen is these signals will have so much energy that they can penetrate and pierce through the ionosphere and go to the outer space. Like they can pierce through the ionosphere and go out. So that also we will take advantage. So but the frequency range should be above 30 megahertz, so it should be above the VHF range. So for those kind of things, this kind of space wave propagation we call it as. So this is not line of sight, this is space wave propagation, where we send the signals towards the space, and they are so much powerful that they can easily penetrate the ionosphere, and they go to the desired place like satellite or some other extraterrestrial object, and they can get reflected from there, and while coming down also they have that much energy to pierce through the ionosphere and come back. So that is space wave propagation. So these are the three main types of propagation. Then one more is this line of sight. Line of sight is like general, the transmitter and receiver should be able to see each other in terms of the radio propagation. So it's optic. If it's optical, I told you, if you are able to see each other, then it is line of sight. So imagine if you can see radio waves. So if you can see radio waves, if you can see that transmitter, then that is the, if you stand on the receiver tower, and if you are able to see the transmitter, then that is line of sight. In terms of C means radio wise, so here the visual horizon is less, like you may be able to see only up to certain distance, but due to the different effects like tropospheric bending and diffraction, the radio horizon is more than the visual horizon. So that is also advantage for us. So these are the basic modes of propagation, very useful. And so what I'm trying to do is I am going in the reverse direction for module 3, because if I start with that attitude and orbit control system, then if I tell the power subsystem, thermal subsystem, then by the time we reach to this communication system and antenna subsystem, you will lose energy. So first I am cracking the difficult one, antenna subsystem. If we are comfortable, then slowly we can go back to the communication subsystem, where we can study the what we can study transponders and what are there in the transmitters. And so transponder is receiver plus transmitter plus amplifier, three things are there, so that we will see. So then we have numericals also in these antennas, we can take very easily. Okay, so I will quickly show within few minutes. So here one important consideration is the angle subtended by the geostationary satellite to the Earth, whole Earth is 17.34 degrees. Okay, so if you have a satellite in the geostationary orbit and if you want to cover from South Pole to North Pole, then the angle it is subtending is 17.34 degrees. So the antenna which we are trying to take should at least offer this much of beam width. Okay, so 3 dB beam width. So then these are different things, we will see them. Yeah, this one 17-degree thing. If you want a global beam, then you have to go for a horn antenna because horn antenna is known for providing large coverage. Then sometimes if you want a focused coverage to particular regions, then there are different options. We will see it later. So the choice for this global beam is usually a waveguide horn or horn antenna. Then all these things, yeah, this one, wire antennas, horn antennas, reflector antennas. All these things we will see in the next class. So as such, the antennas itself is a separate subject, but here whatever is relevant to our subject, we will extract that.